they say for subset model, the regression coefficients are biased estimators. So I'm not too worried about that. I think the most important message in full and subset model is that if you have a big model, the predicted value, the fitted value, will have a large variance. The smaller the number of regressor variables, the smaller is the variance. So we want to have a small model, as small as possible, but then include all the useful ones. So I think that's what I'm interested in full and subset models, and in the comparison. So today I'm going to talk about how can we choose a subset of the regressors. So there are two approaches, but they are completely related. One is based on R squared. R squared is it measures the proportion of variation in Y that is explained by your regression model. Mean square residue is an estimate of the variance of the random error, sigma squared. So if mean square residue is small, then the variance of the regression coefficient will be small. Your fitted Y will also have a small variance. So everything, relates to mean square residue. That is your precision of estimation. So these are the two criteria that I will use to choose a subset regressor variables. Now there are two possible ways of doing it. One is using all possible regression, and another way is to do it stepwise. Stepwise, there are three types: forward, backward, and stepwise. So I'm going to discuss these methods today. So let's go to the criteria for subset selection. Well, there are a number of possibilities, but I think the most commonly used ones are adjusted R squared and the residue mean square. You can also consider other statistics. Some are, like PRESS, we know what it is. Mellow, CP statistics, I may not even have discussed, or AIC. But they are similar in some way. But I'm going to just use adjusted R squared and residue mean square for illustration. So the idea is the same, whether you use the others or not. So here is a graph where I show you the relationship between the R squared and the number of regressor variables P. So if you increase the number of regressor variables, R squared will go up. At some point, in the beginning it will go up pretty sharply, but at some point in time, it will start to stabilize. And at that point would be a good choice for the number of regressor variables. You see, what we want is a regression model with a large R squared. But at the same time, we want to keep the number of regressor variables small. So if you increase the number of regressor variables, you can see the R-squared keep going up. So it's not such a good idea to choose a very small number of regressor variable, because you can improve R-squared significantly just by increasing P to another value. So it is where the R-squared starts to stabilize, that's our choice. Okay? Alright. How about if I were to choose P based on mean square residue? Well, mean square residue actually will decrease as the number of regressors goes up. In fact, if you have, you specify enough regressor variable, you can have a perfectly fitted line. So it will decrease as P increases, and as you can see, choices of P here will not be good, because you can still improve it quite significantly by considering larger P. So usually we choose a P that is near the minimum. Here, I think it might, maybe this graph is not quite right. I think it will continue to go down. So here, the difference for this P and this P may not be that different. So we would choose this P. Remember, we want a model that is as small as possible at the same time. I have a feeling this graph might not be right, because if you have enough regressor variable, the mean square residue could be 0. Yeah, perfect fit. But the idea is to choose a P where you are almost at a minimum and improvement is not likely, not too significant if you increase P further. So now, I'm going to talk about the first approach to select a model. This approach is called all possible regressions. All possible regressions simply means what? All possible regressions. So if you have, let's say 2 regressors, well, you fit all possible models. Y equal to beta naught plus beta 1 x1, y equal to beta naught plus beta 1 x2. That's it. And if you have 6 regressor variables, you would fit 64. You have 64 regression models. And for each of the model, you can calculate either the adjusted R-square or the mean square residue for each model. And then, based on the R-square for each model, we can choose, quote unquote, the best model using either adjusted R-square or mean square residue. So for k regressor variables, there will be a total of 2 to the power k. Each regressor is either selected or not. So let's look at an example to illustrate this all possible regression approach. Now, here is an experiment to in order to predict the heat evolved in calories per gram of cement. So in cement, you have these four important ingredients: tricalcium aluminate, tricalcium silicate, tetracalcium aminoferrite, and dicalcium silicate. All these are some chemical names, you know. If you are studying chemistry, probably you know. So what happened here is you want to create, you know, certain cement that has certain, let's say, maximum Y. Yeah. So you consider 4 regressor variables, and then you want to find out which regressor is useful for the prediction of Y. Alright? So here's the data. There are 13 observations altogether. The response: X1, X2, X3, X4. You know, for cement, what you do is you mix with water, right? And then you can feel the heat. And then you will, people think that cement actually dry up. You know, it will dry after a day or two, and then you have a hard piece of floor. But what I read about cement is this: it actually doesn't dry up. You know, the water, when you mix with cement, it doesn't dry up. The water did not go away. There's actually a chemical reaction with the cement and form a bond there. It's not drying up. It's forming a chemical bond. Yeah. So, a little fact that's interesting to know. Now here we have 4 regressor variables. So we have 16 models altogether. So each regressor, either you include it or not. So it's 2 to the power of 4. Well, here are all the 16 regression models for the cement data. You know, you could choose not to have any of the regressor variable, and that would be your first model, none. None means you choose nothing. So P is 1. So the first one, R squared is 0. You know, you don't have any regressor. So your R squared is 0. Mean square residue is very large. Basically, you are fitting a constant model. You are saying Y follows a constant model, beta model. And then you can consider one regressor model. The next 4 is either X1 alone, X2, X3, or X4 alone. So you fit each of these models and calculate the R squared. And also the mean square residue. Suppose if you want to use mean square residue as the criterion for determining the best model. Or you can consider 2. 4 choose 2. 4 choose 2 is what? In probability you learn, right? 4 choose 2 is 4 times 3 over 2. 6 models. X1, X2, X1, X3, X1, X4, X2, X3, X2, X4, X3, X4. So there are 6 models. Same thing. You can calculate all the R square and the mean square residue. Or you can consider 4. Let me see. 3 of them. 3 of them. 4 choose 3. There are 4 possible ways. So either 4 is not there, or 3 not there, or 2 not there, or 1 not there. Or you can choose all 4. So here's a model where you consider all 4. And you can see that the R square will, it will improve as you increase the number of regressor variables. mean square residue will actually continue to drop. So according to what we have discussed, we are going to choose P where the adjusted R square starts to stabilize, or when the mean square residue doesn't change very much after that. Well, you can, okay, the next page shows you all the regression coefficients. You know, for the first one, you have beta naught and beta 1. For the second model, you have beta naught and beta 2. I guess you can't see very much here. It's just least square estimates for all the regressors.
No, you can still.
Now, here is an R program for us to find this. Well, you could do it manually, you know, say choose X1 to be the regressor, fit a model, and then extract R square and adjusted R square, and then try X2, you know, you can do that. But for 16 models, you will spend quite a bit of time. So in R, there is a function that will allow us to do this very easily. It just automates the procedure. So you fit a model with all the regressors there, and then you can say all out. All out will produce a table that we want. It will contain all the possible regressions, OLS, and so on. So of course, you need certain library for it to work. And then you can write out this table as a CSV file, and this is the file that will be stored. So you can check this out. And it can also produce a plot, which is quite useful for us to determine which is the model that we want. That graph is shown here. So if you have one regressors, one of them is X1, one of them is X2, the other one is X3, X4. So you can see that one of them is the best. It's around 0.6 something. And what variable is that? So this graph doesn't tell you, but you can go back and see. It's X4. X4 is this. The worst one is actually, okay, you can look at R square, just R square, I don't think it matters. And this is X3. Okay? The difference is small. So we know that maybe I should just stick to adjusted R square, okay? So here. So the worst one is X3. So this is X3. The best one is X4. So we know. Then you can also consider two regressors and plot all the 4 choose 2, 4 times 3, 6 of them, 1, 2, 3, 4, 5, 6, 6 dots there. And one of them is the best. Actually, it tells you which is the best. Model 5. So go to model 5. Go to model 5. It will tell you that this, if you use regressor X1, X2, you will get the maximum. So among all these two regressors, X1, X2 give you the best adjusted R square. Now, if you consider three regresses, then, okay, I think I need to move this down a bit. All right, if you choose 3 regresses, then the best model is 11, which is here, x1, x2, x4. So you include one more. This is the best among the 3 regressor models. And for 4 regressors, of course, you use up all of them. So I have labeled it here. So the best one is x4 if you use 1 regressor. If you use 2 regressors, the best model is x1 to x2. 3 regressors is x1, x2, x4. And then the best one is, of course, among, if you choose all 4, then that's the only one and that's the best. So the question is, which one do we choose? Now, I'm not going to choose this because by increasing the number of regressors to 2, I can have a big improvement in the adjusted R square. See, I can have a big jump. So I'm not going to use 1. So the next question is, should we use 2 or 3? Now from 2 to 3, in fact, there's very little difference. Yeah, not much improvement. So I will stay with this. I'm not going to use this. So, final model that is suggested by all possible regression approach is to use x1 and x2. You got that? So you choose a model that there is that the improvement is insignificant if you increase the number of regressors. The textbook also show you a plot of mean square residue versus P. I think I didn't find an R function that can show this, but you can actually plot it out yourself. And based on, so you look for the model that has the smallest mean square residue. So for 1 regressor, it's not too good. Yeah? Better not. This is 1 regressor, this is none. So here is 2 regressors. And the best one, of course, is this one, because it has the smallest mean square residue. So we will, of course, have the same answer. Yeah? x1, x2. And so according to mean square residue, the improvement is not big anymore. So we will choose 2 regressor models. You understand that? Well, so that is the all regressor models approach. This approach is great because you can consider all models and choose the best. Unfortunately, in practice, there is a problem. For example, if you have 2 to the power of 30, let's say you have 30 regressor variables. 30 is not a big number, right? You perform an experiment. You want to predict the income, you look at age, the gender, the household, family members, profession, size, type of housing, and so on. You can have 30, 40 variables. But 2 to the power of 30 models, I just checked with my calculator. is about 1 billion. 1 billion models to consider, you know. So I'm not trying to use R to create a graph for 1 billion regressors. It might take a while. And I don't know how the plot will look like with 1 billion points on this plot. So obviously, there's some problem with this approach. It's not going to work if your number of regressors is big. You don't need it to be very big. 30 already cause you problem. So that's why stepwise regression methods come in. Suppose I have 50 regressors. Maybe I have 1 trillion models. I can use all possible regression approach. So I need to do it in a stepwise manner. So I can either use a forward, backward, and stepwise. Actually, the idea is very simple. So let me explain to you how it works. So let's start with forward selection. Suppose I have k regressor variables. Okay? So that's what we have. K regressors. And the first model that I consider is no regressor. Okay? So better not is in. Then I choose alpha in for determining whether a variable can be entered into a model or not. So alpha in is a small number. It's a cutoff point. Alright, so I choose alpha in. For example, I can choose alpha in to be 0.05 because I'm going to compare p-value with this alpha in. Then I feed models with 1 regressor variable. So I will have k regression models. Now, for each of these models, I'm going to calculate the p-value for testing the significance of xj using the f-test. So I feed a model. I can either use the t-test or the f-test. Let's say I use the f-test. I can calculate the p-value for each of these models. So, of course, all the p-values are different. Some are insignificant with large p-value. Some are significant with small p-value. So, which one are we going to choose as the variable to be in our model? Of course, we are not going to choose those with large p-value. So any p-value greater than alpha in will not be considered as good candidate for inclusion. And there are those that are, and for some regressor variables, the p-values are smaller than alpha in. You know, one of them could be 0.02, one of them could be 0.001. So which one do you choose? Of course, we choose the one with the smallest p-value, the most significant. So the variable that produces the smallest p-value will enter into the model. So now we have beta naught. We have beta naught plus beta 1 x, xj, whatever that is. Now let's just suppose, it doesn't have to be x1, but let's just say x1 gives us the smallest p-value. Yeah? Then what we do next is to consider fitting model of this form. So I have x1 in my model, then I consider x2, or I can consider x3, or I can consider x4, up to xk. So I now have k minus 1 regressor models. Because, so I'm now considering two regressors. And I want to see which one should I include in the model. Again, I will test the contribution of xj after I fitted x1. So I want to compare that model and see which one gives me a p-value that is small enough. Can you follow me? So here, I'm going to consider beta 2 xj, where j plus epsilon, where j is 2, 3, up to k. So I have k minus 1 models to consider. And I'm going to find the p-value based on this test, based on the contribution of xj after I've included x1. All those models with p-value larger than alpha in will not be considered for entering into the model that we want. Only those that are smaller than alpha in will be considered. And some p-value will be smaller, very much smaller than alpha in. Some will be close to it and so on. So which one do we choose? Same thing. We choose the variable that produces the smallest p-value to be entered into the model as the second variable. You got it? So, now, let's say the model that we got after the second step is x4. So we enter x1 and x4 already. Then we consider adding another one. Beta 3, xj, where j is 1, it cannot be 1, it cannot be 4, so it's either 2, 3, 5, up to k. So you consider the third one. And if you can find a p-value smaller than alpha in, you include that one as your third regressor variables. Now, suppose at this step, all the p-values are now greater than alpha in. Then you stop. That's it. You're not going to enter the third regressor variable into it. You got it? So that's forward. You choose one variable at a time. So, let me illustrate this idea using the forward, using this cement data. So remember, we have 4 regressor variables. We want to find out which variable we will pick as the first variable to enter into the model that we want. So step 1, I'm going to fit 4 models. 1, 2, 3, 4. You see? I fit 4 models. And then I look at the p-value for testing the associated regression coefficient. So here's a p-value. 1, 2, 3, 4. So there are 4 models and 4 p-values. Is there any p-value that is larger than alpha in? What is our alpha in here? What's my choice? 0.05. So which regressor variable can be considered in our model as our first regressor variable. Can we consider first one? Yes, because it's smaller than 0.05. This one also. How about this? This is the third regressor. This is 0.059, greater than 0.05. So obviously this is not going to be a candidate that we want. So this model is out. So we can consider this, or this. So there are three possible candidates for consideration. So what's our approach? Well, we take the model with the smallest p-value. This is the smallest. Yeah? So x4 is now entered into the model. You choose the one that is most significantly different from 0. So now, this is step 2. We want to consider the next regressor variable to be entered into our model. Well, we consider x1. So we compare, this model here. This is our model. We already have x4. Now I want to add another regressor. And I want to see the contribution of x1 after I consider x4. So I need to compare with this. All right? So if I compare these two models, I'll be testing for the contribution of x1 after I consider x4. So I can consider x1, or I can consider adding x2 into it, or I can consider adding x3. So now I have three choices. Do I have three choices? Yeah. Okay, so what is the p-value for including x1 after we have included x4? Is this one. For x2, the p-value is this one. For x3, the p-value is this one. So I'm going to line them up properly. So I know I must not consider x2 because the p-value is larger than 0.05. So this one definitely out. x2 definitely out. So I'm left with 2 where the p-values are less than 0.05. So I choose the one that is smaller. The one that is smaller is x1. So I choose the second regressors as x1 because it's the smallest. Okay? You got it? Now let's go to step 3. Step 3, I now have this model. Now this, what I got from the first 2 steps. I have x4 and x1. Now I want to check whether should I include x2 or not. If I consider x2, that's the p-value I get. Or should I consider adding x3? That's the p-value that I got. Now, either one of these produces a p-value that is larger than 0.05. That means we can now stop the forward selection procedure. None of them should be in. And so, no regressor will be added. And the model that we got is this one. Okay? Yeah, it's quite simple, right? If you understand the approach. So I'm doing all this using first principle to show you. But in R, there's a very beautiful function called OLS, step forward. Just now we used the function all possible regression, right? You can just say, you fit the model, and then you just apply this function, OLS, step forward. And then you will perform this step forward procedure for us. It will show this to you. You will say, okay, candidates terms are 1, 2, 3, 4. We are selecting variables based on p-value. And when it's done, it will show the variables that have been entered. Exactly as what we got. x4 first, followed by x1. And then after that, no more variables to be entered. So this is a black box. If you, of course, anybody can use it without any understanding. Yeah? So the difference between a computer scientist and a statistician is that you know how these things are selected. A computer scientist just run it and tell you it's x1, x1, doesn't know what it is. Okay? So that's who you are. So, well, that's forward selection approach. How about backward? Backward, as the name implies, is very similar to the forward approach. Here, you start with all the k regressor variable, and then you specify an alpha out to see which one you can kick out from the model. So you start with everything and then choose this. So it could be number like 0.05 or something. Yeah? And the p-value for testing each xj is calculated. And then you can see which one can be kicked out. Okay, now I am going to illustrate. I'm not going to go read 2 and 3, you can read, but I'm going to show you how it is done with the cement data. So in step 1, remember we have fitted this model already, and here I want to know whether I can kick out x1 or not. So here I don't have x1, so I'm comparing this model with this model. So I'm trying to find out the contribution of x1 after I fitted this. So by comparing these two, I'm looking at the contribution of x1. See this, x2, x3, x4. The full model is x1, x2, x3, x4. So the contribution of this is reflected here. So if this p-value is small, then x1 definitely has a contribution, significant contribution. And alpha out is 0.05. So this one shows that x1 is not so useful because the associated p-value is larger than 0.05. So we can kick this out, x1. But then, what if you have more than one to kick out? Then you look for the one that has the largest p-value to kick out. So you need to consider another model here, x1, x3, x4. So here you are testing the contribution of x2. So next is we consider contribution. So this is one of them. So this is the next one. Consider contribution of x2. So if you compare these two, x2 is here, but not here. And the p-value reflects the contribution of x2. In fact, X2 is even worse. X2 has a very large p-value, 0.509. Also, we can kick it out from the model because it's not too useful. Now, what about X3? So here we consider the contribution of X3. X3 is even worse. It produces the largest, is this X3? Yeah, it produces the largest p-value. Or you can also consider the contribution of X4. So there are 4 models you need to consider. See whether you can kick this out or not. This X4, this is a p-value, also quite large. So, in fact, all 4 of them can be kicked out because of this criterion here. So we choose the one with the largest p-value. Yeah? So we know X3 is the useless one, the most useless one. So kick this out because it produces the largest p-value. Alright, so now after this step, we are left with X1, X2, and X4 after step 1. Then we try and kick out another one if we can. So this is step 2. Step 2 is, see, this is what we had. 3 variables, X1, X2, X4. See here, I want to study the contribution of X3. And the p-value now is very small here. So X3 is significant. Then I can also consider the contribution of X2. You see here, this model, there's no X2. So I'm trying to find the contribution of X2. So X2 produces a small p-value, but not less than 0.05. So it's a candidate that we can kick out. So anything more than 0.05, we can kick it out. So next is we consider contribution of X4. Here, this model. So this is X3, X2, X4. And X4 produces the biggest p-value. Yeah, X4 produces the largest p-value. And so we should remove this one. In fact, this one you must not kick out. It's either this or this. But the one that is the largest will be removed. So after we remove X4, we now have X1 and X2 left in our model. So in the very first step, we remove X3. After second step, we remove X4. And then now, we want to see whether we can remove another one or not. So this is step 3. So we consider removing X1. What's the contribution of X1 after we have included X2? Yeah? And the p-value is very small. Or we can consider the contribution of X2 after we have fitted X1. Again, the p-value is very small. So this shows X2 is highly significant after we have included x1 in the model. This one shows that x1 is highly significant after we have included x2. So neither one of them can be kicked out of the model. So in step 3, that's where we stop. And we say that, all right, the model that we have will be this. Huh? You might notice by now that the model that we got using backward elimination is not the same as forward. Here we have x1 and x2. What about here? Here we have x1 and x4. No, they may not lead to the same answer. But are these two good or not? x1, x4, x1 and x2. Let's take a look. Take a look at this graph here. Okay, take a look. I think both are quite reasonable. So here is x1 and x2. If you expand it, can you see another little dot there? So there are two here. So one of them is x1, x2. One of them is x1. What's the other one? x1 and x4, right? So there are two there. They're very close. So let's take a look. Let me erase all this. So let's look at x1 and x2. The other one is x1 and x4. So forward selection give us this. Backward selection give us x1, x2. And both of them are not too, both of them are quite reasonable, right? Both of them choose the top two. And where the difference is very small. I think if there's a bigger difference, then you will probably get the same answer for forward and backward selection. All right. I'm not going to take a break because I want to discuss the last approach, and then that will be the end. So no need a break. If you want a break, you can go anytime. So I want to talk about stepwise, the third approach. You see, forward is you choose one in, second step, choose another one in, third step, choose another one in, until you cannot enter anymore. Backward is you start with the whole model, and then you start throwing out one of them, and then another one, until you cannot throw out anymore. You stop. Stepwise is, hey, you know, first step, we take one in. You started out like forward selection. Take one in, and then second step, take another one in. Let's say first one is x1. Second one that you took in is x2. Now, you got two already, right? Then the third step is, now you got x2 now. Maybe you don't need x1. So you check. You check now. Can I eliminate x1? x1 is the first one entered. x2 is the second one entered. But now, before we consider the next one, let's try and see if x1 is needed. If x1 can be kicked out, we kick it out. And then we proceed. So each time, after you take in a new one, you consider all those in your model, see whether you can kick it out or not. If you can, yes, kick it out. If not, you proceed as a forward selection method. So that's how stepwise regression works. So here, we need two things. You need alpha in, alpha out. I have to choose a very big value here for illustration. Okay. Alright, step 1. Step 1 is choose a variable to be included. Yeah? So this is just like forward selection. So x1 is this, x2 is this, x3, where's the x3? Oh. x3 is this one, x4 is this one. So x4 is added. You got it? Now I'm doing stepwise, alright? Next step, since I only have x4, I don't have to consider kicking x4 out, right? It doesn't make sense. So now I consider adding x1 into it, x2 into it, and x3 into it. So I already have, I have x4 now. I want to find out whether, let me just shade it to know where we are. So I have x4. So I want to see which other variable I can get in. So this is forward selection. The one that gives us the smallest p-value will be accepted. So this is forward selection. As you can see, x1 has the smallest p-value. So now, after step 2, we have x4, x1. So I'm going to shade it now. x1, x4, and x1. Now, if you are going to do forward selection, you continue for the third variable. But this is stepwise. Stepwise means, okay, I got this first, I got x4, and then I got x1. Now in stepwise, you now check whether you can throw out the one that you entered earlier or not. Maybe with x1 we don't need x4. So you now do a check on the variables that you already have in your model. So step 3 is like backward now, doing backward. So you consider the contribution of x4 after you have fitted x1. Can we throw this out now? You see, the p-value is very small, not sufficient for you to kick out. So here I'm considering the contribution of x4. It has a very small p-value. So in step 3, we will not delete x4 from the model. So now, my model remains the same as x4 and x1. So after step 3, I still have x4 and x1. I found that I cannot delete x4. Then I go on to look for the next variable. The next variable is to consider whether I can kick out anything or not. I can include any one or not. So can I include x2? Can I include x2? Or can I include x3? So these are the two models that I fit. Well, here x2 gives me a p-value of 0.05. This one gives me a p-value of 0.06. In fact, according to alpha in of 0.15, remember we have a bigger alpha in here. So, both of them can be in. Both of them can be in at step 4. So we choose the smallest p-value less than 0.15. So now, after step 4, we have x4, x1, x2. You got it? So now we have 3. Then we go on. The next step is to see if we can kick out the old ones or not. So we just got x2 in. Now I want to see whether I can kick any one of these out or not. So this is what I have now. I want to see whether I can kick x4 or x1 out. Okay, so well, that's easy to find out. So here is to check the contribution of x4 after I filter x1 and x2. This one is to check the contribution of x1 after I filter x2 and x4. So this gives me a p-value of this. This gives me a p-value of this. So can I kick out any one of them? Anyone that has p-value greater than 0.15 will be kicked out. So in this case, I am going to remove x4 because x4 is now not significant if I look at x1 and x2. So with x1 and x2, hey, the old one, x4, we don't need anymore. So we remove it. So after step 5, we have, so we can remove this. We now have x1 and x2. Okay? So now we have x1 and x2. And we just throw out x4 to get this model. So what's the next step? The next step is to consider more variables to come in. Now we don't have to consider x4 because you just kick out x4, right? You can consider it if you want to. But now we will check whether x3 should be in or not. So this is a forward again. So after we did the backward here, we do forward again. So x3, you can check, you can also check x4. I'm sure you will kick that out. So this one is 0.2089. So can we add this or not? We can't, because the p-value is now greater than 0.15. So the final model obtained is x1, x2. Right? And you can also use this function both for stepwise regression. He will just show you this. He says enter this, enter this, enter this, finally kick out x4, so you are left with x1 and x2. So it shows you what happened in between. Okay, that's the end. So, so today I have discussed all possible regression approach, all possible regression, stepwise. Stepwise, there are 3 types of them, and they are all quite simple, actually, the idea. Alright, I think that's the end. Let me just say a word or two about the final exam. I am not saying too much because
no context.
Okay. So we have 10 chapters here.
Do the same. Using this
Chapter 1 will not be tested. That's for sure. It's just module policy. I label it as chapter 1 so that you will read it. And you, I think the exam is next week, right? If I'm not wrong. Saturday, 9 a.m. So what happened here is you already got 20 marks from your quizzes. 20 marks from your midterm exam. Final exam will be 60%. So it's an exam paper with 60 marks. Closed book exam, all topics covered, although slightly more emphasis will be given to later chapters. But chapter 3 is still very important. You can use calculators, graphics, whatever. I don't check, I don't care. Some tables will be provided. I don't think you need it. I don't know. I forgot. And one A4 size help sheet. You can print it, you can handwritten it, but no stick on because you increase the surface area. That's not fair to others. And do not write with a pencil. It's not allowed. It has to be a pen. And the paper comes on one side blank, so if you don't have enough space, you can just write on the other side. Also, you know, from my past grading experience, when I say give a brief justification why, for example, X4 is included in the model, you know, for the forward selection. Give a brief justification why X4 is included. I expect an answer like, you know, the p-value associated with testing X4 has the lowest p-value. You know, short sentence. But sometimes I see students write 4 or 5 lines to justify. Let me tell you how I grade. If you say X4 is included because p-value is the smallest, you get, let's say if it's 5 marks, you get 5 out of 5. If you write 5 lines, the first line is you talk about something else, and then another line about something else, then the final line is you choose it because the p-value is smallest, so you got 5 marks. Then I read the other sentences. If you make any mistake in other sentences, a mark will be deducted for each error that you make. Because I cannot let you say false and true, and then I have to choose the true answer for you, right? So remember, the more you write, there is a possibility of more marks being deducted from your answer. Because every mistake that you make is subjected to a penalty. So I advise you not to write too much. Just write to the point. Sometimes I give you very little space. I purposely put very little space. Just enough to write 1 or 2 lines. Some students try to write 1 whole page. Continue, you know, write 1 whole page on the other side. It's totally unnecessary. Because every time I read carefully. I look for errors. Any error, 1 mark off, 1 mark off. Until
He brings up a decent point.
I can give you negative, but never. It will be 0.
You can write like
So,
multiple statements.
please also, okay, so write concisely to the point. Don't write too much. It won't help you. And write in a way that I can read. That's another problem. Sometimes I have problem reading. The writing is so bad, you know, that I cannot read. If I cannot read, I cannot give you any mark. I try my best to read. After reading for 5 minutes, still cannot. 0. That's it. Because I don't understand what you write. I cannot read the handwriting, means 0. So it has to be legible. I must be able to read it. Okay, another thing is there will be 5 questions in the final exam. Many parts test on, most of it tests on understanding of concepts. I don't think you need too many formulas, right? You know, it's not a memory test. It's a test of understanding. If you understand what is flying, you can do this problem. If you understand what is forward selection, you can work out this problem. You don't need any formula. In fact, I don't need any help sheet to work it out. Put it this way, maybe 1 or 2. So it's a test based on understanding of concepts. All right. There are many problems that test fundamental ideas. Pretty simple. So I think if you work on it, you should be able to get a B quite easily. If you want an A, you need to work on a few parts that are a little bit more challenging. In fact, the more challenging one is for students who want to get A plus and A. If you do well, I think you can get A minus. So that's what I think I want to say. Is there any question? Is there any question? Okay, well, this is the last time I'm teaching this course. Next semester I'll be teaching probability. That will be my last time in NUS. I guarantee you that. I'm retiring, for sure. I've already booked my air ticket to America to see the autumn foliage in October. So I'm not teaching next semester, for sure. Anyway, I enjoy teaching all of you. It's fun, to meet all of you. And I wish you all the best. Okay?
Thank you.
All right. Thank you. Bye. If you have any questions, please email me. I'll be available.